This is illustrative math. Algebra 1 supports Unit 5, Lesson 9, interpreting functions. Let's describe the domain of a function based on the context it models. So the whole point of this lesson is to determine whether graphs are continuous or discrete and to interpret functions and analyze their domains. The first activity is a notice and wonder. So take a minute to pause and write down something you notice and something you wonder about this data and these graphs. All right, so you should have already written down what you noticed and wondered. I'll go over what I noticed. I noticed that one graph has points or dots, and the other graph is a line. I noticed that both have negative slope. I noticed it's the data from the table in both graphs. And I noticed they're both linear. And then for wonder, I wonder what the data represents. I wonder why one is points and one is a line. I wonder if it's the same data, but maybe it represents two different things, two different situations. So I'm wondering what that could be. That pretty much covers activity 1. Think about if there was anything you noticed or wondered that I did not pick up on. Activity 2, connect or not. So we have 3 basic instructions here, and then we have 4 situations. Here's 1, 2, 3, 4, that we have to follow all these 3 instructions for, okay? So for each one of those situations, we're going to make make a table of at least 5 pairs of values, of input and output values, that represent the relationship given. Then we're going to plot those points from the table, labeling the axes on the graph, and then we're going to explain whether the points should be connected and explain if there are any input or output values that don't make sense. So basically here we're going to be explaining domain and range. Remember, domain is the possible input values or possible x values. And the range is the possible output values, the possible y values. Another way to think of it, because the input values are the independent variable, your domain represents possible inputs or possible values for the independent variable. The range represents possible values for the dependent variable. And then let me just label this one too. This is independent variable. All right, so let's keep all that in mind and look at this first situation. A cab charges $1.50 per mile plus $3.50 for entering the cab. The cost of the ride is a function of the miles m ridden and is defined by C of m equals 1.50 m or 150 m plus 3.50. So I get to pick my input and output value, or I get to pick my input values here and then calculate my output values. The first thing I want to do is figure out what's my input, what's my output, which is my independent variable, what's my dependent variable. So I notice it tells me the cost of the ride is a function of the miles ridden. And I know when I have a sentence about a relationship written that way, blank is a function of blank, that means that the first thing they're telling me, the cost of the ride, is the dependent variable. And the dependent variable is a function of the independent variable. So the cost is a function of miles, and the miles are the independent variable. So independent variable would be what gives us our input, which makes sense because C of m, C would be the cost, the output is the cost, and our input is our mileage. So take a look at your equation here. If you think back to the previous algebra lesson, or actually not the previous algebra lesson, if you think back to previous units where we looked at linear forms of equations, I can see this is written in slope-intercept form. This is a linear equation written in slope-intercept form, and I can tell from looking at it I could make a graph, but I'm actually going to make the table first and then use the points from my table to make the graph in order to follow the instructions here. So let's just pick some easy input values. If I travel 0 miles, 1, 2, 3, and 4 miles, I'm going to calculate the costs. So if I traveled 0 miles, that would be C of 0, and it would be equal to 150 times 0 plus 350. So what I did was just plug in my input value into my equation for m. And then I represented it here with function notation. You can see my input replaces my variable for m there. All right, so if I calculate that, of course, this would become 0, and I would just have 350. 0 plus 350 is 350. So my output would be 350. C of 1 would be 150 times 1 plus 350, and that would be equal to 5. C of 2 would be 150 times 2 plus 350, and that would be equal to 650. And you can see the pattern here. We're just adding 150 each mile, which makes sense because each additional mile costs 150 extra, as the problem tells us. So I can go ahead and fill out the rest of this. And then my next step in the instructions was to graph the points. First I need to label my axes. My independent variable will go on my horizontal axis. So this is miles, or mileage. It's miles traveled. And then the dependent variable would be on my y-axis, or my vertical axis here. Let me erase this to get out of the way. My dependent variable is my cost in dollars. And then it looks like I have about 20 like tick marks here that I could use. So since my table values only go up to 10, I'm gonna make every 2 be worth 1. So basically I'm going by 50 cents here. My intervals on my horizontal, my intervals on my vertical axis, I'm going by 50 cents. All right, that's a little high. It should be right there. All right, and now I can graph my points. If I travel 0 miles, it's going to cost $3.50, which is a point right here. 1 mile would cost $5. These are going by ones. 1 mile is $5. 2 miles is $6.50. 3 miles is 8. Is that right? Yep, there we go. And 4 miles is $9.50. So I can see there's my points. Linear, looks right to me. Now I have to do the third part. So we made a table of at least 5 pairs of values. We plotted the points and labeled the graph. Now we need to answer, should the points be connected? And are there any input or output values that don't make sense? So when you're considering if the points should be connected, you need to consider your independent variable and think about, would it make sense for my independent variable, my x-axis, would it make sense for it to have all continuous numbers or just whole numbers? So should I be connecting these points or not? Can I have miles that are not whole numbers? The answer, of course, is yes. I can have miles that are not whole numbers, right? You might travel 1.5 miles, you might travel 6.38 miles. So it does make sense to connect the dots here. And I'm just going to write that out. Connect the dots, connect the points. Because it's possible to travel partial miles. Okay. Oh, and then the final thing to explain possible domain and range. For domain, I'll just use a D. For range, I'll use an R. Possible domain, I would say all positive numbers. Positive because you can't have negative mileage. And then possible range values, all positive numbers. Not going to have a negative cost, right? All right, number 2, very similar to number 1. The admission to the state park is $5 per vehicle plus $1.50 per passenger. Total admission for one vehicle is a function of the number of passengers. So total admission is a function of number of passengers. So here we have our dependent variable as a function of the independent variable. And it's defined by this equation here. So this is what I'm going to use to fill out my table. Again, I'm going to pick some easy inputs. And if I were to plug in these values, it's gonna cost $5 plus $1.50 per person. So it wouldn't be possible to have a vehicle of 0 people traveling through the park, but if you did have a vehicle of 0 people, the base cost for any vehicle is $5. 5 plus $1.50 times 0, that should be a 0 there, would be just $5. And then for one person, I'm paying $5 base cost plus $1.50 for that one person, or $6.50. And if I just continue adding adding $1.50 per person, that's It's $8. I can see this is going to have the same rate of change, the same slope as the previous one. So very similar problem here. Now I need to think about my graph. My independent variable was the number of passengers, so people in the car, and then the dependent variable was the cost in dollars. Graphing my points, let's see, looks like I need to go up to 11, so I'll just go by ones on both axes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's sorry, that's not my first point. That's going to be when I have 4 people. My first point for 0 people would be 5. 1, 2, 3, 4, 5. Yep, right here. And then 1 person costs $6.50. 2 people would cost $8. 3 people would be $9.50. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. Yep. 1, 2, 3, 4. Okay, so $9.50 right here for 3 people, and then $11 for 4 people. All right, so the last thing I need to do is discuss, should I connect my points? Would it make sense to connect them, or should I keep them as just points? Again, you want to consider your input. Does it make sense to have a partial passenger? No, it does not make sense. I cannot have numbers in between whole numbers here. I can't have 1.5 people going into the park. I can't have 3.75 people going into the park. So you do not connect the points because people are countable. You have to have whole numbers. You can only have whole numbers of people. All right, and then to answer the last part, we have to discuss domain and range. So possible domain, that would be all positive whole numbers. And I'm saying whole numbers because, again, number of people has to be a whole number. We can't have negative people, that's why I say all positive numbers. And then for the cost, again, we're not going to have negative cost, so I would say all positive numbers greater than 5, since we did have a minimum of 5 there, right? Our minimum cost is $5. Greater than 5. And range, again, is about the output, the dependent variable, possible values for that. Domain is the possible input values, possible independent variable values. Moving on, number 3. This one's a little different. It's exponential, as you can see. It says this new species of mice is introduced to an island, and the number of mice is a function of the time in months since they were introduced. The number of mice is represented by the model b of t equals 16 times 1.5 to the power of t. And it tells us number of mice is a function of time in months, so we know the independent variable is time in months. The dependent variable is how many mice there are. I'm going to pick some easy inputs again. 0 months would be when the mice are first introduced. If I plug in 0 into my function, b of 0 is 16 times 1.5 to the power of 0. Remember, anything to the power of 0 is just 1, so this is just 16 times 1, or just 16. Sorry, that's a times. Then if I plug in 1 for t, b of 1 is 16 times 1.5 to the power of 1. I'd get a value of 24, 16 times 1.5. And if I just continue this process, and you could totally use a calculator for completing those powers there, you'd get 36 after 2 months, 54 mice after 3 months, and 81 mice after 4 months. And I just use a calculator plugging the equation in to determine those values. Now let's graph it. Number of months, time in months was our independent variable. Dependent variable was number of mice, or mice population. And our points go all the way, we need an output going all the way up to 81, so I'm going to go by 5s on my vertical axis. So this would be 5, 10, 15, I'm going to label, how about I label 10s? 30, 40, 50, and then 80. Okay, and then these I'll just go by ones. So at month 0, when we start, we have 16 mice, and then month 1, we have 24. Month 2, there are 36. Month 3, there are 54. Month 4, there are 81. 1, 2, 3, 4. all the way up here. So I can see it's exponential. It's starting to increase as it increases. Now, I connected the dots there. Why would you connect the dots? What do you think? Remember, we are looking at the input and considering the input when we determine whether or not to connect the dots. The input is time in months, and time is continuous. So I would connect the dots because it's possible to have 1.5 months, right? 1.2, or it's possible to pick any day, any time of day, and any number of those months, and the number of mice could vary. So it's not like all of a sudden on month 2, boom, there's 36 mice out of nowhere. Throughout the month, the number has increased. So we connect the points, or connect the dots, because time is continuous. Time, our input, is continuous. And then for the possible domain and range, domain would be all positive numbers. We're not going to have negative values. Range would be all positive whole numbers, because you can only have a whole number of mice. Number 4, it's another exponential relationship. Think about a piece of paper. The area of the piece of paper is going to be the length times width. If you fold it, the area of what shows, like what you can see, is half of that, right? As each fold cuts the paper in half effectively. So the area is cut in half every time we fold the paper. So this tells us the area is a function of number of folds, which means area is our dependent variable, number of folds is our independent variable, and then here's our equation that represents the relationship. So thinking about what we learned in our previous lesson and the regular form, the form of an equation for an exponential relationship, I can see that my initial area is 93.5, and then my growth rate is 1/2. So that makes sense, because as I'm folding it in half, I'm cutting the area in half. So I'm going to go ahead and use my same values for input, just to keep it easy. So if I have made 0 folds in the paper, my area is 93.5 inches. If I, and actually it doesn't tell me inches, but I know that it's inches, because the paper is 8.5 by 11 inches, right? After I fold it one time, that area has been cut in half, and it's 46.75, and then cut in half again, cut in half again, and continue cutting in half. After 4 folds, my area of paper is down to just 5.84 inches. All right, so I'm going to go ahead and count by 5s again on, let me label my axes first. So my vertical axis is my output, right? That's my area. And I'm going to count by 5s, as I said. So going up 2 tick marks is 10, 2 tick marks is 20, since I'm going by 5s on the tick marks. Oops. 60, 70, 80, is that right? 10, 20, no, I messed something up there. Hold on. Okay, so this is 10, 20, 30, 40, 90, there we go. Okay, and then 1, 2, 3, 4. Okay, 0, 93, about there. 1, after 1 fold, it's cut in half. Oops, a little bit above 45. After 2 folds, it's cut in half again, so we're about here, 23. At 3 folds, we're at 11, and at just over 11, and at 4 folds, we're down to just barely over 5. So I can see the exponential function forming there. We can see that typical type of shape. And then to think about if I should connect the dots, think about your input. Would it make sense? I forgot to label the input. This is number of folds. Would it make sense to have a partial number of folds? No, it would not make sense. So do not connect the dots, because you can only have a whole number of folds. It's either folded or it's not. So domain, possible domain, all positive whole numbers. And then possible range values. Oops. I'm rushing here because the bell's about to ring. Possible whole numbers. And then the range is the area, so that would be all positive numbers, because area does not have to be a whole number, okay? All right. Moving on, we have one last activity here. We just described the domain and range and what the graph would look like basically if it's continuous or discrete. Would it be a continuous line, or would it be discrete, as in just points? Weight of a puppy is a function of time. Weight of a puppy is the dependent variable. The time is the independent variable. And then time is our independent variable. Time is continuous, so it would be connected. Number of winter coats sold in the store would be our dependent variable as a function of temperature. Our independent variable, temperature, is continuous, so this would be connected. Our independent variable is continuous, so it would be connected. Number of books in the library is a function of number of people. Number of people is our independent variable. Number of books is our dependent variable. Number of people can only be a whole number, so this would be discrete. It would be dots, not connected. Height of water in a tank is a function of volume of water. Volume of water is our independent variable. Height of water is our dependent. Volume of water is continuous. It can be any number, so it would be connected. Amount of oxygen in the atmosphere is a function of elevation. Elevation is our independent value. Amount of oxygen is dependent. Elevation is just a number. It's continuous. It can be any number, so it would be connected. And then thickness of a folded piece of paper is a function of number of folds. And number of folds is our independent variable. Thickness of paper is dependent. So this would be discrete or not connected, because number of folds would have to be whole. And that's it for that lesson.